So here is our last topic for test 2. And technically, there's nothing new here. There's nothing new calculus-wise. We're going to be applying what we know to something different. And what is that difference? Well, so far, everything we've done has dealt with functions. However, functions aren't the only thing that exist. There's also just straight up equations. So, for instance, how about a circle? Now, the equation for a circle is x squared plus y squared equals r squared, r being the radius. And the circle I have here is radius 2, so that's why we get a 4 there. You can't solve this for y and get a circle, because a circle is not a function. It fails the vertical line test. One input can have multiple outputs. It's not a function. So if this isn't a function, then how could we figure out the slope at some point? Well, we can still do that with derivatives. And before we do that, I want to point out quickly here that if we have, say, this notation here, and we want to take the derivative, what that technically is we're taking the derivative of both sides. So this is exactly the same as, say, adding 2 to both sides. But instead of adding 2 to both sides, we're going to take the derivative of both sides. And then that's what this notation means, this operator lingo here, saying take the derivative. And so on the left, we would slot our f of x up into the notation there. And then on the right, we would actually do this derivative then, because the derivative of x squared is 2x. And this is everything that we've been doing. But I want to make clear that technically, we are taking the derivative of both sides. It's just that the left side, we're using this symbology here to indicate this is a derivative, and then this is actually our derivative. So this is the symbol that tells us we have a derivative, and then this is actually the derivative. And we're going to do the same thing. Is we're going to take our circle, and we're going to do the same thing. We're going to take the derivative of both sides. And that's our first step. How are we going to get the slope of this circle? The slope of this tangent line I have drawn here? Well, we will take our equation and take the derivative of both sides, which is what we've been doing all this time. So we'll do this derivative now. And first off, the derivative distributes. And so I'm going to do that. I'm going to distribute the derivative to each term in there. And we don't need that parentheses anymore. And on the right side, the derivative of a constant is always 0. So on the left side, I distributed the derivative, and on the right side, I actually did the derivative. So let's keep going. So the derivative of x squared, well, we know that. That's 2x. And now here is what would be considered new here. This is technically, though, the chain rule that we're going to do right here. And this is the expression I want to talk about for a moment. So I'm going to leave it like this. That's still mathematically correct. We just haven't actually done the derivative yet there. So I'm going to be rigorous with this first, and then I'll show you the simple way to think about this. But let's say I'm just going to call this a new function. So I'm just going to say this g of y is this y squared. And now what's the big problem here? Well, the big problem here is that the derivative operator is saying take the derivative with respect to x. And that's never been a problem before because all our functions have been a function of this variable. But now we have a y here. And so these letters are different. We have an x and we have a y, which indicate these are two different variables. And so we just can't blindly say this is 2y because we need to take the derivative with respect to this variable x. And so how we're going to do that is let's just label this as gy, and then we're going to use a chain rule. So like a chain rule over here on the right. But instead of writing it the way it is on the right there, instead of df dx, I've named this function g. And we do ultimately want the derivative with respect to x. So we have this function y squared, and we want to take its derivative with respect to x, a different variable. And we do that with the chain rule. And so the chain rule says, well, we'll now have df du next. Well, I'm not using f here for this function. Whoops. I'm actually using g for the function name. And u in a chain rule, in this case, is actually the y. And then we multiply this, according to the chain rule, by then dy over dx. And that's just the chain rule. But look at what the chain rule says here. The chain rule says if you want the derivative with respect to x, then the first thing you do is take the derivative with respect to y. And that's just the normal derivative that I've been calling for the chain rule here. It's just a straight up derivative. So there is our 2y. But the chain rule then says, well, you now have to multiply by dy dx. Well, we don't know what dy dx is. As a matter of fact, that's what we're trying to solve for. And so we leave this notation as is. So here we actually did the derivative, the dg dy, but we don't know dy dx. That is, in fact, what we're solving for. And so we leave this symbology here to indicate this is what we're solving for. We're solving for this derivative. So going back to where we left off, the derivative of y squared with respect to x is 2y dy dx. And I'm just going to pull that down here. And remember, our goal here is to find the derivative. And here it is, dy dx. That's the symbol for the derivative. And now we just solve for it. So we'll subtract minus 2x from both sides. Then we'll divide both sides by 2y. The 2's will divide out, and there's our derivative. And that is the derivative of a circle. So this blue line right here, if I wanted to know the slope, well, I'd have to give the point of interest here. So for instance, I'm just going to guess and say that looks about, say, 3/2. And let's say that height is also 3/2. So if we want to know the derivative at this point, well, then we'd have to plug that stuff in. So I'm saying x is minus 3 over 2. And then I'd be saying y is also 3 over 2. And so then a derivative at this point is minus 1. So the one thing, well, there may be other things, but the one major difference here is that all our previous derivatives were a function of one variable, just x. With implicit differentiation, our derivatives will no longer be of one variable. Because if they were of one variable, then we could solve it as a function. So it's a big difference here. To actually find this derivative, we do need to know the x and y points. We can't just use one point anymore. So the short story of this right here is if your letters are different, you take the derivative normally, and then a chain rule says you multiply by that derivative with respect to x. So that's the short of it. If the letters are different, x and y, different letters, which mean different variables, you take the derivative normally, so y squared is 2y, but then the chain rule says you have to multiply by the derivative of the argument. So again, this is what I've been trying to emphasize with the chain rule. It still works the same. The first factor is the straight up normal derivative, and then you multiply by the derivative of the argument. And the argument in this case is y. Y is what you're putting into this function. So it's all consistent. Everything you've learned to this point, all the math, all the terminology, it's all consistent. It's just being applied now to an equation instead of a function. So let's check out another example. How about this? We want to know what is this derivative with respect to x. So what are we going to do first? We're going to take the derivative of both sides, which is what we normally do, which is what we've been doing all this time. We've been taking the derivative of both sides. And if you like to write stuff out, that'd be a good first step to write. And the derivative of a constant is 0. And then the derivative here, I will distribute into the parentheses here. And now that I've distributed, I don't need those parentheses anymore. And there's a good second step. Now notice we have x squared, a power function, times another power function of a different variable. A function times a function means product rule. So here is a product rule, and here is a product rule. So let's check those out independently. Let's check this one out first. And so we're saying that this is the product of two functions being multiplied together. We then explicitly state what those functions are. So we're saying f is x squared, and we're saying g is y. And then like we've always been doing, I can't stress enough, nothing has changed here. We're just taking all that you've learned so far and now applying it to an equation. So once we have f and g, we then take those derivatives with respect to x. So with respect to x, this is also an x, so the letters are the same, so that's just a straight up derivative. Derivative of x squared is 2x. Now for the derivative of g, and I'm just going to write this to be perfectly clear. We're doing the derivative of g with respect to x. And so here's a y, here's an x. The letters are different, which means the chain rule kicks in now. And so if we want this derivative, well, the derivative of y, the straight up normal derivative of y, is 1. And a chain rule then says, then you multiply by the derivative of the argument. The argument is y, and then here is the symbol for that derivative. Now 1 times doesn't change anything there, so I can just get rid of that. But that's our answer. Remember, we're trying to solve for dy dx. We don't know what this is yet. So we have to keep this symbol here so that we can solve for it. And those are our pieces then for this product rule. So if we look at this then, and looking at the product rule, we're going to have f, which is x squared, and then times g prime. Now g prime is dy dx, the unknown derivative that we're trying to solve for. And continue on with product, then that's plus f prime, which is 2x, times g, which is just y. And there's our completed product rule. Now going back to the original equation, which is right here, let's do this other product rule here. So here's our other one. And we're going to explicitly define f to be x and g to be y squared. And once we've explicitly defined that, we then take those derivatives. And the derivative of f, the derivative of x is 1. And now the derivative of g, and I just want to be explicitly clear here again, this is technically dg over dx. So we have an x here, but a y here. The letters are different. The chain rule is going to kick in. So we do the derivative normally. So the derivative of y squared is just 2y. And then the chain rule kicks in and says, now you have to multiply by the derivative of the argument. The argument in this case is y. And there is the derivative of the argument. Again, we don't know it. We're trying to solve for it. And we can't solve for it if we don't have a symbol to solve for. So that's why we're keeping this here, because that's ultimately what we're solving for. And so now we can write this out using the product rule. So we have f times g prime, which is 2y dy dx. And then we have plus f prime, which is just 1, and then g, which is y squared. And that's our answer. So we have this product rule up here we finished, and this product rule here. And let's now plug that in to where we left off on our original problem. So I'm just going to copy this here. This is for the x squared y. So I'll go down here. So for the x squared y, we just figured that derivative out. It's that. And now for the xy squared, that's this one, xy squared. So I'll just copy this and stick that in for the derivative of xy squared. Bang. There it is. And here is our full result. Again, our goal is to solve for dy dx. And now you just kick in some algebra skills. How do you solve for dy dx? Well, you isolate it. So this 2x, 2y, we'll move this to the right side and get rid of it as we work on isolating dy dx. So that was 2xy, right? Yep, 2xy, moving it to right side, make it negative. This y squared, we can also move this to the right side. And now we have our dy dx's all on the left side. And now what we're going to do is just factor this out. And let me leave that as a step, actually, right there. So now what we're going to do is factor the dy dx. So there's a dy dx in this term. There's a dy dxt here. We're going to factor it out. And this messes with people sometimes because this is not the greatest common factor. The greatest common factor of these two terms would also include an x. But we're not interested in the greatest common factor right now. We're interested in dy dx. And so we will only factor this out. To get that expression. And we're done. Because all we have to do now is divide both sides by this to get our derivative. And there's our derivative. And really don't like that 2 sitting there. I'm just going to stick that 2 there. Doesn't that look so much nicer? But that's our final answer. That is our derivative. So here is Desmos, nice little handy graphing tool. Here is the function we just did. And I thought this was kind of an interesting function. It's not a function, actually, these equations. These equations can get pretty crazy looking. Some of them are actually very interesting. But if you look at this equation here, you can see it looks like a plus sign with this line going through it. But if you actually zoom in and zoom in and zoom in and zoom in, you can see, though, at the origin, there's some curviness happening there. And this is what we just figured out the derivative for. We just figured out the derivative at every point on this function. It's an equation. In other words, it's going to be hard for me to break function because we say it so much. These are equations. They are not. None of these things will be functions in implicit differentiation. So I thought that was pretty interesting to look at. So let's try out another one. We want to know this derivative with respect to x. And we do the same thing we've been doing all this time. We take the derivative of both sides. And that's a good first step to write down. And the next thing we can do is the derivative distributes. So let's do that. Let's distribute the derivative into the parentheses. And now that we've done that, we don't need the parentheses anymore. And on the right side, we will also distribute this derivative into the parentheses. And once we've distributed, we don't need the parentheses. And there's our next step of work. All I did was distribute the derivative. So let's do these. And first off, let's recognize this very first derivative here has a constant, and we can pull that outside the derivative. Also recognize this is a product rule. So we're going to define f to be x and g to be y. Once we define those pieces, we take the derivative with respect to x. Again, that's a crucial thing. What you take your derivative with respect to is absolutely important. All these derivatives are with respect to x. The derivative of x is 1. And then, what is the derivative of y with respect to x? Remember the chain rule. You take the derivative normally. The straight up derivative of y is just 1. And then the chain rule says you then multiply that by the derivative of the argument. The argument is y, and we want to take the derivative of that with respect to x. And those are our pieces. And so if we look at our product rule here then, we're going to have a 2 times everything, whatever we get here. So I'll just put a big bracket there. And we're going to have, then looking at the product rule, we're going to have f, which is x. We're going to have g prime, which is dy dx, plus f prime, which is 1, times g, which is y. And that's our derivative for that piece. So here's our original function again. And here's that product rule we just figured out. So right here, derivative of 2xy, we just figured out it's that. So we did the first derivative there in the first term. So let's do the next one. The next one, the derivative of y squared with respect to x. So we take the derivative normally. The straight up derivative of y squared is 2y. And then the chain rule says multiply by the derivative of the argument. And then that's dy dx. Remember here, y is the argument. And so dy dx is the derivative of the argument. And that completes that derivative. Moving on to the other side of the equal sign, the derivative of x. Notice these are both x's, so just a straight up derivative here. The derivative of x is 1. And now here's another thing. I'm just going to falsely use an equal sign really quickly here, but the derivative of y with respect to x. Remember, you take the derivative normally, so the derivative of y is 1, and then you multiply by the derivative of the argument, dy dx. That is our derivative, but there's something else I want to show you here about how this notation works. Is remember that whatever the operator is connected to, by the way, this is not multiplication that connects these things. This is operator lingo, which you'll learn more about in the future. But what's nice about this notation is we can slot this y right up into the operator, and bang, there's our dy dx. It's all logically consistent. That's what's so awesome about math. And there we go. We have officially done all the calculus. Now what's left is to solve for dy dx, which is that algebra. And how are we going to do that? Well, we're going to gather all our dy dx's on one side so that we can isolate it. First thing I'm going to do here is distribute this 2 back in here so we can separate these terms out. So I'm going to stick that 2 in there. And because we distributed, we don't need that parentheses anymore. And this 2y, let's move it to the right side to make it negative. And this dy dx right here, let's move it to the left side, which will make it negative on the left side there. Whoops. And there we go. We've isolated all the dy dx's on one side and all the other junk on the other side. And now to solve for dy dx, we will factor out only dy dx. So we're going to factor out a dy dx from all of this stuff. So we're going to factor out all these dy dx's here. And there we go. Factored out that dy dx. And now we're done. We just have to divide both sides by the parentheses to get our derivative. And that's our answer. So there was a couple of product rules we've done so far. Let's check out a quotient rule. So here's our function, and we want to know what is the derivative of function. And here's an equation. Equation, again, these are all equations here. If I say function again, ignore it. These are all equations. None of these are functions. So we're going to take the derivative of both sides, like we've always been doing all this time. Take the derivative of both sides. So that's our first step. Let's take a look at the left side first. So the derivative of y squared with respect to x. So we get a chain rule here because the letters are different. So the chain rule says take the derivative normally. So the derivative of y squared is 2y. And then the chain rule says you then multiply that by the derivative of the argument. And there we go. Now the right side here, let me just copy that because this is going to be our chain rule here. Let's look at that. And let's define our f and g. So we're going to say f is the numerator and g is the denominator. And then once we explicitly define that, we'll take those derivatives with respect to x. So the derivative of x is 1, and the derivative of minus 1 is 0. And then for the derivative of g, the derivative of x is 1, and the derivative of plus 1 is 0. So that's all simple enough. And let's put those together now to get our quotient rule. So again, we got the quotient rule bottom right here. So we have f prime, which is 1, times g, which is x plus 1. And then this is minus, since there could be multiple terms here, let's be cautious and use a parentheses because of this minus sign right here. So now we have f, which is x minus 1, times g prime, which is 1, so unaffected, all divided by g squared. So g is x plus 1, and we're squaring that. So there's plugging in our information for the quotient rule. And in a numerator, we have x minus x, so that subtracts out. And then we'll have 1 plus 1 to get us a 2. And that's our derivative for that quotient rule. So let's go back to where we left off. Here's our function again. We didn't finish off the right side, but here we did. There's our answer. So I'll just plug that right in. There it is. And then to solve, we're just going to divide by 2y. So if we divide both sides by 2, that'll cancel out this 2 over here. And divide both sides by y, we'll stick it around here somewhere. And there's our derivative. So what would Calc 1 be without some trig functions? Let's check this out. We want to know the derivative with respect to x. So what do? We take the derivative of both sides. And that's our first step. And looking at the right side, because that's simple enough, the derivative of a constant is always 0. And on the left side, let's distribute the derivative into the parentheses. So just going to distribute that in there. Now that we've distributed, we don't need that parentheses anymore. So there's our next step of work. And let me copy that, paste it here. So the derivative of x, now there's 2 ways you could think about this. The derivative of x is 1. Another way you could think about this is this x will slot right up into the notation, and anything divided by itself is 1. Another way to look at why that's 1. And now we have to do the derivative here of this tangent. And I want to look at this one separately. So let me just copy that out of there. And let's take a look at that separately. So first off, what do you see here? What do we have to do this derivative? Well, notice we have a function times a function. We have a power times a power of different variables, which means inside the parentheses here is a product rule. But this product rule is being placed within a tangent function, which means chain rule. So we have a chain product going on here. Now for the chain rule, we do the outer function first. So the derivative of tangent. What's the derivative of tangent? That's secant squared. And a chain rule says, cool, you took the derivative straight up. Now you have to multiply by the derivative of the argument. So what is that? So we get a product rule here. And just xy's, I'm just going to look at the product rule right here. If you can imagine in your brain, x is f and y is g, then we can read off what the product rule is going to be here. So the product rule says f times g prime, remember g is y, so times the derivative of y, plus f prime, so that's the derivative of x, which is 1, plus g, which is y. So I did just brain power out this product rule, which is something I'm going to do more on test 3, and hopefully something you're slowly working towards as you do more practice. So let's look at, then, where we were. We wanted to know this derivative of tangent xy. We just figured that out. That's this expression. So we'll just take that and paste it right in. I have to say, in this respect, math is a lot easier that I can just copy and paste stuff in. That's pretty handy. Our goal is to solve for dy dx. Remember, our goal here is to get the derivative, and here it's sitting right here. This is where the notation is sitting. This is what we need to solve for. And so we need to start isolating this, which means we are going to have to distribute this into the parentheses. So we can get rid of this parentheses and separate this out. So I'm going to distribute that secant squared in there so we can get rid of the parentheses. And is that going to be, there we go. So all I did was distribute there to get rid of the parentheses. And now we're going to isolate dy dx, which means we're going to take this whole term, move it to the right side, so that'll make it negative. And we have a 1 sitting here by itself that will move to the right side. I'll make that negative. And I'll just leave that as a step of work right there. Because our last step now is just to divide everything sitting in front of dy dx. And that's our answer. The only thing I would do to clean this up is that this y looks, again, this is, beauty is in the eye of the beholder. I think this y looks ugly after a trig function. So I would put it in front of it and say with this x, that's ugly. Put it in front. So, obviously that's up to you, but there you go. There's our final answer, our derivative. All right, so I got one more here. And again, I try to not only do some easy medium problems, but I also want to show you what the difficulty level is of the book, because I do think you should know, hey, how hard are these going to get? So here's the last problem in the book for these problems, and let's check it out. We want the derivative with respect to x. What do we do first? We take the derivative of both sides. So there's the first step I'll write in. Take the derivative of both sides. Now the left side's easy enough. This is just a simple chain rule here. So the derivative of e is always itself. And then the chain rule says multiply by the derivative of the argument. The argument's 2x. That derivative is 2. And there's our derivative for the left side. Now on the right side, what do you see? What's going to happen when we do this derivative? Is there a product rule? No. Is there a quotient? No. There's no division. It's just a straight up chain. So, well, let me write this out. Let me leave it like that, actually, so I can show the steps. So a chain. So we first identify the outer function here, which is sine, and that's the derivative we'll do first. And the derivative of sine is cosine. And the chain rule says, cool, you did the straight up normal derivative, and now you have to do the derivative of the argument. So let me distribute the derivative into the parentheses. And I'll leave that as a line of work there. And the derivative of x is 1. And of course, again, we can always slot whatever's sitting there up into the notation like that. Anything divided by itself is 1. And the derivative of 3y with respect to x, so the 3 is a constant. We can pull that outside the derivative. And the y, we can just slot right up into the notation. And that's where we're at. Now our goal here is to solve for dy dx. So we're trying to isolate this and solve for it. We're trying to get the derivative. And so the first thing to isolate that would be to divide both sides by this cosine. Let's get this off the right side. Whoops. There we go. And now that there's no more multiplication on the right side, we don't need that parentheses anymore. And to continue on isolating dy dx, we'll subtract 1 from both sides. And now finally, we'll divide everything by 3. And there's our derivative. I have to say, for the final problem in the book, that's actually not too hard. There might be harder ones, maybe even squeezed in, because ultimately this was just one chain rule. So the previous problems, I think, were actually harder than this one, where you had 2 products, or a product in a chain. So that's the last example problem there, but if you recall from the last video, I said there was another way to do those problems that we were doing. So for instance, x raised to the x. Remember, in that last video, we talked about using inverse function properties to solve this. However, oops, that did not get in the right side there. However, that's not the only way we can do that. So let's check this out. Another thing we can do, and this is another good, clever manipulation, is what we can do is we can take the log of both sides. Now, why do we introduce the log? Because the log has the property that we can take this exponent and bring it down into the base. And that's a very useful property. And so now what are we going to do? Well, we're going to use what we just talked about today. Let's take the derivative of both sides. Let's do the left side. We have log of this function. What's the derivative of log? The derivative of log is 1 over the argument. So the derivative of log here is 1 over the argument. And then the chain rule says, cool, now you have to multiply that by the derivative of the argument. And that would be then df. So I'll just say that again. The derivative of log is 1 over the argument. That's what this is, 1 over the argument. That's the derivative of natural log. And then the chain rule says multiply that then by the derivative of the argument. So the argument is f, and so df dx is that derivative. And that's the left side. Now what about the right side? Well, we have a product rule here. We have a power function times our log function here. And so looking at the product rule, we would have f times g prime plus f prime times g. That's the derivative of x log x. And notice here that x divided by x divide out, so that's 1. That's the derivative. So now our ultimate goal is to solve for df dx. And so how do we do that? Well, we'll multiply both sides by f of x. So we'll multiply both sides by f of x. And we're done. The last thing we need to do is determine what is f of x. Well, that was given in the starting the problem. F of x is x to the x. And so our final answer here then is that. Let me do one more of those from what we did in the last class there. What was another one we did? How about x raised to the x plus 1? Let's do this one with what we've learned today. So how would we do this? Well, we would take the log of both sides. And again, why do we do that? Because we want to use the properties of log to pull this exponent out of being an exponent. And that is what the properties of log allow us to do. To bring that exponent and bring it in front of the log. And now that we've done that, we'll take the derivative of both sides. And here we go again with the derivative of log of the function. Again, the derivative of log is 1 over the function. So the derivative of log is 1 over the function. And then times the derivative of the argument. And there's our left side. And now on our right side, we have a product times a log. A power times a log, which gives us a product rule that we have to do here. So, the product rule says f times the derivative of g plus the derivative of f, so this derivative here is 1, times g log x. And that's that derivative. And now we will multiply both sides by f of x. And then finally, we'll recognize f of x is actually x raised to the x plus 1. And that's our answer. And if you want to look back to the previous work we did in the last lecture, you'll find we got the same answer. So, what's the point of showing you these two ways to do the same thing? And the point is that these are useful maneuvers for calculus. Not just what we're doing here, but for more that you will see in the future. So don't get wrapped up in, why is he showing us two things to do the same thing? That's not the point. The point is for you to see these maneuvers so that you're familiar with these maneuvers and you know how to do them more in the future. Because you will encounter these types of maneuvers if you are going more into calculus. So what did we do last time? Last time we used the properties of inverse functions. So just to clarify, in the last lecture, we used the property of inverse functions, which means we raised this to e to the log, and then we stuck our function in there. That's what we did last time. That's a clever maneuver that can help in cases. And then what we did this time is we took the log of both sides first, and then we took the derivative of both sides. So either way, a log is coming into play here. We're using the useful properties of log and also the properties of inverse functions. So useful maneuvers, that's why you're learning these different ways for the same thing. It's more to show you these maneuvers and so that you can get comfortable with them. And in the next video, we will talk about then test 2 review.